Hello everyone, I'm Daokun from Hunan University in China. I shall be speaking here about an evaluation of hash indexes based on persistent memory. We provide a comprehensive evaluation of persistent hash tables. In particular, we focus on the evaluation of 6 state-of-the-art hash tables with real PM hardware. Our evaluation was conducted using a unified benchmarking framework and representative workloads. Besides characterizing common performance properties, we also explore how hardware configurations affect the performance of PM-based hash tables. With our in-depth analysis, we identify design trade-offs and good paradigms in parallel and suggest desirable optimizations and directions for the future development of PM-based hash tables. Until now, various types of persistent memory based on different physical mediums have been proposed. The hash table, a fundamental component in many software systems, can benefit from the new features of persistent memory to achieve high performance and instant recovery. There has been a new breed of hash tables specifically designed for persistent memory. But it's unclear how well this proposed hash table perform on real persistent memory and how they differentiate from each other if a wide range of performance metrics are considered. Because persistent memory was not widely available and their experiments were based on DRAM emulation mostly. Inspired by existing work, here we conduct a comprehensive evaluation of hash tables on a system equipped with Intel DCP-MM. We use a benchmarking framework that is an extension of PyBench. It provides a set of interfaces and a unified testing environment for fair comparison. We evaluate PM-based concurrent hash tables from both macro and micro perspectives. In addition to commonly used metrics such as throughput, latency, load factor, LLC misses, resizing overhead, memory usage, and recovery overhead, we also consider the impact of persistent memory hardware such as bandwidth and various combinations of instructions. We choose 6 persistent memory-based hash tables. They are converted from DRAM counterparts or specifically designed for real persistent memory hardware. They have various structures like separate chain, open addressing, or extendable hashing. They use different synchronization mechanisms such as lock-based or lock-free, and distinct resizing strategies such as dynamic or static. And they employ different cross consistency mechanisms. We extend PyBench and Intel PCM to make an evaluation, and conduct our experiment with 6 DCP-MMs. Finally, we conclude the design trade-offs, good paradigms, and desirable optimizations. The first insight, we conduct an experiment to evaluate the throughput and bandwidth of 6 hash tables. We use 32 threads to insert 16-byte key-value pairs. We also conduct an experiment to evaluate the throughput and bandwidth in a situation that data is written to PM directly. This is an ideal situation because there is no hash computation and there is no need to maintain state structure. Soft reached the max throughput at 19 million operations per second. The ideal throughput is 28 million operations per second. Under this situation, the fence and flush instructions influence the throughput lightly. The average bandwidth is 5 GB per second, but this is much lower than the upper limit of PM bandwidth, which is 13. To figure this out, we extend this experiment by adding 2 accessing granularity. We pack 4 pairs and 16 pairs into a batch. Key-value pairs in a batch are written to persistent memory sequentially. By this way, The granularity of accessing persistent memory grows to 64 bytes or 256 bytes. When the byte size is 64 bytes, the throughput grows to 18 million operations per second. When the byte size is 256 bytes, the throughput grows to 140 million operations per second. Thus, we can conclude that the low throughput is mainly due to the random small write. Random small write is the inherent access pattern in hash tables. Even with specific optimizations to address this issue, such as reducing the number of random writes, the performance of existing PM hash tables is fundamentally constrained. We argue that new hash table designs are designed to mitigate the detrimental effect of random small writes and achieve higher performance. The second insight, we break down the total amount of data written to PM when inserting 200 million key-value pairs. We can observe that for the 3 lock-based PM hash tables, the extra data induced by locking is tremendous in size because of frequent invoking of locks and contention among threads, reaching 12 GB or 32% of total data on average. Memory allocators also cause severe write amplifications, which may be far beyond our expectations. Key-value pairs occupy only 10% of all data written to persistent memory. We cannot ignore write amplifications caused by memory allocators and serialization primitives. In the future, for a PM-based hash table, we must design PM-friendly memory allocators and serialization primitives. For read operation, we measure the last level cache line misses and reading bytes per operation. Combined with throughput, we can see that log-free reading less data per operation and writing less read can improve throughput substantially. We can leverage fingerprint or hybrid memory design to reach launching less reads and read fewer cache lines. The fourth insight is the resizing scheme. Full table rehashing is harmful to concurrency, leading to low throughput and unexpected latency. In the future design, dynamic extendable schemes and lock-free resizing are good paradigms to alleviate the overhead of resizing. In all, there are 4 insights. The first one is avoiding random small write in future design. The second one is design PM-friendly memory allocators and serialization primitives for hash index. The third one is launch less read and read fewer cache lines. The fourth one is avoiding full table rehashing for each resizing. We also hope that in the future, persistent memory can have more efficient accessing granularity, especially for small size writes. Meanwhile, we hope some work can improve the performance of lock and allocator on PM. And there are efforts to reduce consistency and durability overhead and programming difficulty. Thank you so much for your interest and attention.